Hello and welcome. My name's Tim Marshall. I'm chair of the RTS Thames Valley Creative Technology Centre. It's our mission as a centre to stimulate a conversation between technologists and the creative community. Recently, we had a session on artificial intelligence. It was significant that when one of our speakers, Professor Yanis Andropoulos of UCL, was asked what his advice would be to the next generation of broadcast professionals, he suggested that they learn a bit of coding. Furthermore, in the past year, I've been approached by 2 students interested in joining our centre. Their discipline? Guess what? Computer science. It's clear then that digits are playing an ever-increasing role in our broadcast environment. So I'm all the more pleased that we are returning to the subject of machine learning for this session. Our speaker today is a long-standing member of our committee, Tony Orme, and he'll be looking at some of the ways in which machine learning is being taken up in the broadcast environment, as well as a prophetic word on where it might be going in the future. Tony.
Thanks, Tim. I'm editor at the Broadcast Bridge, and as Tim said, I'm a long-standing committee member of the RTS Thames Valley Technology Centre. I'm an associate tutor in broadcast engineering at the University of Surrey, and I'm also studying for my PhD at the University of Surrey. In my current research is IP timing anomaly detection using machine learning. So I've got a bit of a foot in both camps of machine learning and IP, and they do work together beautifully. So the objectives for this talk are to provide an overview of what ML is and is not, to discuss 10 applications of ML, and explain neural networks and why we use comparisons to the human brain. I'll also be describing the ML training process, and discuss data sets and why they're so important. So what problem does ML solve? And I think this is one of the most challenging aspects of understanding ML is why do we bother? We've got computers that we can program using linear code, but the key to understanding machine learning is it's all about the data. So the machine learning allows computer algorithms to find patterns within data sets to provide classification or predictions based on unseen data. So by that, I mean that we don't have to program lots of if, else, and then statements to try and understand what's going on in the data and have prior knowledge of the problem we're trying to solve. We can take the data and apply it to a neural network, and the neural network can work out what's going on. I mean, that's an oversimplification of what's happening, but that's essentially what we're trying to do. So we're moving the responsibility of creating a prediction or classification model away from the programmer to the actual data itself. And the people mostly involved in this particular application now are data scientists who spend a lot of their time training and optimizing models to provide the best possible outcome. So what ML is not, it's not magic. Despite what you may hear in the media, on the news, it's really a massive scientific discipline with a lot of mathematics behind it. It relies on hours or even days or weeks of training, and it's heavily compute intensive for the training process, that is. And when we talk about machine learning, there are 2 aspects to machine learning. There's the training, and then there's the evaluation. So the end user who has an application running on their computer, their desktop, or a server, when they're using it for a particular application, will be using the evaluation part of the model, or the evaluation part of the solution, whereas the vendor who is training the model, the data scientists who are training the model, are using a much more intensive part of that model, which allows them to train the data set to be able to provide the predictions that the user has at the end. So these are my 10 applications which I think are quite relevant to broadcasting. They're in no particular order. I just chose them as they came into my head. So the first one we have is detection of models for media classification, and then searching for content, video compression, quality control, ratings and media recommendations, automated editing, highlights creation, closed captioning, remote camera operation, and IP network optimization. So just taking those one at a time, the detection of objects for media classification for a library ingest is incredibly interesting. It's no secret that many broadcasters have to move off tape, and any of their archive and libraries that are already on tape have to be moved very, very quickly, because we've run out of VT machines. They're not being made anymore. The parts are proving difficult to get, and we have to transfer everything into digits. But digitizing our media is only one half of the story, because data storage is only as good as data retrieval. And so this is an opportunity to actually start adding metadata to our images, to our media. And ML is a perfect application of this, because the machine learning algorithms can be taught to actually inspect the video, inspect the images, and to learn particular traits within the video, to find scenes, to find, you know, like it's like it's a sunny afternoon in London. It can also detect audio, so we can have speech. It can detect speech. It can translate that speech into text. And so the more metadata we have, the better opportunity we have to actually search the data and to find the media we want. One of the disciplines that is used for this is convolution neural networks, which we'll talk about in a little while. So the other flip side of the coin of library storage and archiving and metadata tagging is library retrieval. So we producers, journalists want to be able to extract, and editors want to be able to extract all of that data and be able to use it to find the images they want. And so we have things like long sentence tagging. So traditionally we may have typed something in like Houses of Parliament, but now we can sort of extend that and say Houses of Parliament on a Sunday afternoon in the middle of summer when it's sunny at 3 o'clock in the afternoon. And if somebody has ingested that material and they've put the necessarily ML algorithm in there, which has been able to determine all of those aspects, those metadata tags are added to the video, which allows you as a user to then find that video later on. Natural language processing is a big aspect of being able to pull out the data as well, because one of the other things we assume is that we have to type data, our requests into the computer itself, when really we can actually talk to the computer. So there's no reason why the conversation I'm having with you at this moment, an ML engine can't take my words and then turn them into text, which can then be stored. And you quite often see this in some YouTube videos as well with automatic subtitling. But we can also pull multiple resources, so we're not stuck to one library. We can pull data from all kinds of different libraries which are joined together. And then we have visual object character recognition. So in the image on the right there, the appropriately trained ML engine will be able to determine there's a chair or there's a window and a particular type of chair. And the more data we use to train these systems, the better they are at determining and classification, or determining the objects and then being able to provide the appropriate metadata afterwards. Video compression is a massive field in machine learning. And one of the great advantages of ML is that it's being researched by scientists and researchers who are working outside of traditional television broadcasting. So you might find scientists working in the medical environment, or trying to find images, because medical relies heavily on having high resolution images. So the kind of research they're doing in that field will have applications in broadcast television. Part of the video compression is object movement detection. So here we can see a bicycle which is being found by the ML engine. And when you can start doing object detection, you can then get better compression. Because transferring lots of pixels is a very inefficient way of sending data. We can go into HDR estimation and color prediction. So again, we can use our the patterns within the data to be able to determine what's actually going on and be able to pull information out so we can better classify it. And it's important to remember what we're trying to do here with ML is look for patterns, but predictable patterns. Because if I throw a ball up in the air, I can say with a certain guarantee it's going to land again in my hand. I'll probably catch it. And if I keep throwing the ball up, I'll keep coming back down to earth and I'll keep catching it. If I throw a ball up, I don't expect it suddenly to disappear off to the moon. So in other words, a lot of the things we do in our natural life are heavily predictable. And it's these patterns and these predictions that the machine learning algorithms, the models, use to be able to do their training and then their predictions thereafter. So quality control is quite interesting because, again, there are two aspects of quality control we generally use in television. There's the technical standards. So we need to find out if a video image is breached a peak white or it's gone below a black level. And whether an audio has gone beyond a specific loudness level. But the other aspect of quality control is subjective assessment. So this is when we can actually look at the images. And traditionally, we relied on people, on humans to do this. But with machine learning, we can train the systems to be able to actually watch the picture to see what is going on. And we have the image here that you can see on the right. The question is this creative intent or is this an error? And the machine learning should help us provide that kind of subjective assessment and find out what's going on in the picture. So ratings and media recommendations is something you may have seen on your set-top box or on Netflix type programs where you have the thumbs up. And again, this is a case of big data. So we're gathering lots of data from the viewers, and not only are the sort of media companies pulling in our own specific data, they're pulling in lots of other data as well. So they're pulling in information about our viewing environments, you know, the demographics of the people watching the programs. And then they're able to put all this data together to provide better recommendations and better predictions so that we can all find out what we should be watching. So item 6 is automated editing. Because machine learning can effectively read images, it can see images using the sort of more the philosophical idea of being able to learn images. It can also provide basic cutting facilities as well. Again, this is a part of machine learning which is in its relative infancy, but you can take lots of different images from lots of different sources and gets the ML to build you up a program, and you can type in a script, and the ML engine will provide you a very basic cut of what's going on, so you get a rough cut. In the field, we can have live ad insertion. So again, through ML, we can look at the kind of programs people are watching, where they are, which country they're in, which towns they're in, and provide ad insertion on the fly. There's highlights creation, and there's areas where the ML engine is detecting areas of interest within a crowd, for instance. In a stadium like this, there's no reason why we can't have hundreds of cameras around the stadium, all watching the crowds for reactions and being able to establish what's going on, so that the highlights can be created and slow-mos can be created on the fly. And we can create atmosphere tracks all through having cameras going into neural networks. Then there's a closed captioning and subtitling, which has been used for some time. And this is where the soundtrack is being listened to, if you like to use that phrase, by the ML engine. And in this case, it's a natural language processor, NLP. And that language is then turned into textual data, which can be inserted through the subtitling machine. And again, this is incredibly clever, because it's not just about detecting voices, but also that we can have language translation as well. So again, it's all about the data. And if you feed one of these machines enough data, then it can actually start doing language translation for you. And another example of that is Google Translate. So if you could use that on the fly, then you can start having lots of different closed subtitle translations. And this is one of the favorite ones for me because of its potential, is remote camera control. So with facial recognition, I've seen some demonstrations where we have cameras around a stadium, and we can program a camera to, or we can train an ML engine to detect certain faces, so a particular player in that field, and tell the cameras or a series of cameras to track that one player. So we've always got that one player actually on the available to be taken to air. And that's the form of automated tracking. Now, where I think this gets really, really interesting is I see a time in a studio where the director will be able to call the shots, will have some kind of NLP which will detect the voice, turn that into a textual data, and then be able to send all that data to the camera to tell it to then track a particular player. So this has a lot of applications I see in sports, and I think it's a really interesting way of going forward. I've not seen anything like this working yet, but I can assure there's technologies there to do it, and I'm sure people are working on this kind of application. And this is my all-time favorite, IP network optimization, and this is the subject of my research for my PhD at the moment. And what I'm doing here is detecting network congestion, so we can get better use of data within a network, a generic IT network, that is. Specifically, I'm looking at the internet. So we can detect the long flows and short flows, route them better, and doing that through machine learning, where we can detect the establishment of these flows very quickly and then be able to provide the necessary routing. There's also a lot of work going on in networks with security intrusion detection. So we will see a lot of denial of service attacks, for instance. The ML programs sat on the networks will be able to detect those, or if people are suddenly clicking on a lot of links within an email, for instance, or something similar to that. So there's a lot of work going on within machine learning and computer security. So we quite often hear people talking about the comparisons to the human brain, and what exactly do we mean by that? Why do we draw a comparison between ML and the human brain? And again, this is at a very, very basic level. So I'm not in any way, shape or form suggesting that ML engines are as clever as the human brain, because they're not even close. They barely scratch the surface. But the analogy of how they work is very similar. So if we think of the human brain as a biological interconnect of billions of neurons, as we learn as humans, we change those interconnects. They're added together, or they're removed or updated. And the more training we give to the human brain, then the better it is predicting the outcomes. And here, the specific text I've written is, the more training data the human brain has, then the better it is at predicting outcomes that the senses have not experienced before. And that's a really important aspect for machine learning, because what we're saying here is we're giving a small set, or not a small, but an extremely large set of data to the machine learning engine, or to the human brain. And from that data, the human is able to extrapolate and interpret other scenarios it hasn't witnessed before. And an example of that is how we teach a child to cross the road. So when we're teaching a child to cross the road, we don't teach the child how to cross every road in the world, because that would simply be impractical. Instead, what we're doing is providing them with a training for a generic set of roads. So we say, this is how you cross a road. But then the child, and then becomes the adult, is able to take this training and can be used to cross all roads. And I think that's a really important sort of aspect of how you get your head around the whole concept of ML, because that's the whole point of training, is we're not training the model to understand every single possible outcome. What we're doing is training a subset of every possible outcomes, and then allowing the model to use the knowledge it's found, if you like, to be able to extrapolate that and find the other outcomes. In the same way that when a child learns to cross the road, it's unlikely that parents will teach the child its very first outing to cross a road in Oxford Circus. But after a bit of practice, maybe a number of years of practice, the child or young person will then go to Oxford Circus and be able to cross the road before, having never actually seen it before. In the same way, they'll be able to detect a bus before, because when we're born, none of us know what a bus is. It's only through compounded learning and continuous teaching and training that we're able to detect a bus, but not only just a red London bus, but usually any bus within the world. So this is how the whole concept of machine learning works. It's the repetitive training that we can provide, which allows the model then to be able to see other or be able to predict other outcomes based on information or scenarios it's not seen before. And that's a really important aspect. So these are the comparisons to the human brain of how the actual model learns. Now, it's important to sort of say at this point, I'm really only talking about supervised learning. There are two aspects to machine learning, something we call supervised and unsupervised. Unsupervised is it's like a superset of the learning. Really, we have to understand supervised before we can start even thinking about unsupervised. But for the purposes of this talk, we're going to just talk about supervised learning, which is a major part of the way we use ML in broadcasting. So we start with a training set with labels, and the training set, if you like, is the parent teaching the child and saying, you know, look left, look right, when there are no cars, cross the road. But the important part of this is that the training set we're providing, we're telling the machine, the algorithm, what the outcome is. So each training record, if you like, within the set, and there could be typically 10,000 records within a set, each one of those records will have a label. And that's and these can apply to anything. This can be a part of video processing, it could be part of language processing, it could be part of classification. So for instance, if you want to detect all buses in a scene, you would present the algorithm with 10,000 pictures of buses in various angles and colors and sizes, with labels saying that red bus, London bus, Manchester bus, Glasgow bus, and through a process of training, which I'll describe in a moment, the algorithm is able to learn and differentiate between those different types of buses. And the really interesting thing is that we don't need to tell it where the bus is in the image. We just have to say there is a bus there. And over a period of training and time, the neural network will be able to then classify those buses. And not only that, but if you present it with an image of a bus it's not been trained with, it will be able to determine what type of bus that is. So this is where the object recognition comes in. Now, once we've taken the training set, we then put it to the neural network. We process it through the neural network through a process called forward pass. And that's quite important, because that's just presenting the data to the network, and the network then calculates the output. And we use that output, which is effectively a label, and compare it to our label value of the value we know to be correct. So the neural network will calculate a value for us. We then compare it to the known value, which we know to be correct, and we end up with something called an error. And that error is then used to train the network. And in the network, we have only two things we can change, only two parameters we can change. We can change the weight and we can change the bias. And I'll come on to those in a short while. But essentially, when we train a network, all we're doing is this repeated task. And this repeated task of throwing all of the data of training sets, getting it to calculate the forward prediction, comparing its output to the label it already has, and then updating the existing weights and biases based on that error, and keep doing that 10,000 times. And then each of those 10,000 times, we may do another 1,000 times. So we have tens of thousands of data points we're passing through the network, so that the intention is, as the network becomes more proficient and it's effectively learning the data set, its error will become smaller and smaller and smaller. And when it gets to an optimum level where it can't get any smaller, that's when we say the network is trained. And at that point, we can then pass other data, so other images through it of, say, other scenes with buses in them, and it will be able to find a bus, even though it's never seen that image before. Why is ML so powerful? And I've used the phrase the programmer here, and I did deliberate over this for some time to whether I should say the programmer. But it's essentially the person who is building the network, I concluded here. So the person who is actually building the network doesn't need any prior knowledge of the problem they're trying to solve, because essentially what they're trying to do is take a data set and apply that data set with its known outputs to the model so that it then tends towards a minimum. And when that error loss gets to the lowest minimum it can, then we say the model is trained. And so through a process of learning, the model is able to find patterns to help with classifications and predictions. And those are the two kind of things we're trying to do with machine learning. We either want to classify something, so we want to say, you know, in the example of a library, we'd want to say, well, this is this image consists of the Houses of Parliament on a Sunday afternoon, and it's sunny, and there are 3 red buses going past. That's all methods of classification. And a prediction is something like we do in natural language programming, where we would have a sentence which say the cat fell off and then what is the word after that? And the system would be able to predict that the next word is mat. So we have this method of being able to build a system where we're not actually programming the outputs. What we're doing is we're providing a data set to a model, which is then finding the patterns we want to find within that model. And we can then use that to be able to find other predictions on data it hasn't seen before. So what is a neural network? Graphically, this is a single neuron. And anybody who's looked at how our brains work will notice some of the sort of aspects of this which are similar. We have on this particular single, and this is just one single neuron of a model. And you can see we have a series of inputs. So on this, we just happen to have 5 inputs. The W's are the weights, and they're effectively like a multiplier. And the bias is a DC offset, which is like something we add as an addition. And then we sum all that together, and we have what we call an activation function. So on the output of the sum there, we'll have a value which ranges between sort of a small minus figure and a big minus figure. And then a small minus figure and then a small plus figure. And then the activation function decides whether that output becomes live or not. So not all the data is passed through, and if it passes a certain threshold, which the activation function defines, then that neuron may fire or not. So if we take a single neuron and then we start stacking them up to provide a network, we have something like this image here. And this is so simple that it probably doesn't actually do anything, but it just shows graphically of what's happening within the neural network. So here we've got 5 inputs with each of our weights and biases, and each one of those inputs goes to a hidden layer, which is another neuron within the network, and then each of those hidden layers goes to the output. So a typical neural network could have hundreds of thousands of these actual neurons inside it. I say this one is very simple because we're just trying to show pictorial of what's happening. And the type of models we have, this is by no stretch of the imagination exhaustive. It's just a basic list of the models that you may come across when people start talking ML to you. The first one is recurrent neural networks, or RNNs. And these are traditionally used for sequence predictions, such as in speech or data. So when we talk and when we process language in machine learning, we think of it as a sequence prediction because one word comes after the next. The convolution neural networks is something which is used in image data, because the convolution part of the network is looking at spatial relationships within an image. GANs, the general adversarial networks, are heavily used with video prediction. And again, they're unsupervised, so it's not something we generally get too much involved in, because they get really, really clever very quickly. But those are used quite heavily in video prediction. And then we have LSTMs, long short-term memory sequence prediction, and time series analysis, and that's something I'm using heavily within my own models I've been building for the TCP predictions, flow predictions. And then the final one is transformers, and they're an advance on LSTMs. So each one of those is just one of those type of images, but a lot more of it and a lot more complex. Fundamentally, they all work in this way, where we have our neural network, which consists of weights and biases and an activation function, but they get very, very complex very, very quickly. So how do machines learn? Well, I hope by now you've realized it's all about the data set. Nothing else matters other than the data set. Well, it's not strictly true, obviously. The model certainly matters. But the most important aspect of what we're trying to do with a machine learning is that we have to provide it with an initial data set. And it's the data set where data scientists spend most of their time. So when I was building my models for the TCP flow prediction, I would say 80% of my time was spent within the data set, analyzing it and trying, and then sort of setting the labels and the classification data, and then the data that could be fed into the network in a manner it understood, so that it could then predict give me the classification outputs. But also, who owns the data? And that's not a flippant question. It's actually a real question. In academia, it's quite easy to do machine learning, because there's a lot of data sets available, which are available to people doing academic research. It gets a little bit more interesting when we have to build commercial products, because you can't just download a data set and then use it in your commercial product, because that is, there are various license restrictions stopping you doing that. Some you can, but you've got to be very, very careful about the licensing agreement that you're using for the data set. So again, a lot of what we're doing in machine learning is creating data sets, and data sets can be all kinds of things. They can be images of footballers on a football pitch. They can be recordings of footballers, or any event or a motor race or whatever. It's wherever you have images, text, sound, you have a potential data set. But if you start taking pictures of people's faces for later image recognition, as I described with the camera, then the person who owns the face may have a view on whether you're allowed to use their face to train your model or not. So it's something you have to be very, very careful of. So as I mentioned earlier, there are two aspects of what we're doing with machine learning. First of all, there's the training of the model. And once we've trained the model, then we have to be able to use it. And the model, after it's trained, is essentially the same model as the one we trained. It's the same design. Now, as I said, this is a very simple neural network here. In reality, this would be incredibly complex, and it's something the data scientists would design. But it's the same model which has the weights and biases loaded into it from when we did the training. And it is able to take previously unseen data as its inputs. So again, looking at the buses, we provided images of 10,000 buses, so that now if we provide an image of a bus that the model has never seen before, it will be able to recognize that the image has a bus in it. And we call this method evaluation. So we have training, which is the application of the data set thousands of times so we can update the weights and biases. But the actual forward prediction, the actual making of the model do something useful and practical for us, we called evaluation. So the evaluation consists of this forward propagation to be able to calculate our classification result or our prediction result, which ends up being a number or an image or a sound sample or whatever we've designed the model to predict or classify. So the key here is to realize that the training model that we've provided through our hours or days or weeks of training then becomes our evaluation model. And although training could take days or weeks, the actual evaluation takes only a few milliseconds, because the time of training of updating those weights and biases requires a lot of resource from a computer. It's heavily computer intensive, and because of the kind of mathematics we're using, it's using a method called backwards propagation, which uses a form of calculus to be able to then predict what the weights and measures should be and to optimize those and to get them correct to be able to build our model. But once we've calculated those weights and biases, we don't have to do it again for that particular model. So we can just use them within our forward prediction, which means it's much quicker at predicting the output. So this is what an ML program looks like. And this is the one I use in my own code. And you can see that's the top here, the prediction out, where it says equals model brackets X data. That is it. That is the bit that is doing the actual forward propagation. So that is the model. The X data is the data that's already been provided, and you've seen the labels are there as well. So the loss next part is it's taking the output of our model and comparing it to our known set of labels and providing us with a value. And then we use that value to what we call backwards propagate, which is then to calculate what our weights and measures should be. And then the optimizer step just updates those actual values themselves. So that's all there is to it. That is essentially an ML engine. The interesting thing about this one is inside that one line of code, there are 263,000 neurons in that particular model. So calculating the weights and measures of and biases of 263,000 neurons is a processor intensive task. And you may have heard that we use GPUs a lot in training, in ML training. And that is mainly because there are two aspects of a GPU that we're interested in, coming from the graphics industry. And that's linear algebra, which is used in graphics ray tracing, which also is used in machine learning. And then there's parallel processing, which is fundamental to graphics processing. So it just so happens that GPUs excel in both of those. And now GPUs, there are some vendors building GPUs that specifically build or put ML type things, accelerators into their designs. But fundamentally, these are the two aspects of a GPU ML scientists are interested in. And that's what it does. That prediction out equals model X data, that is passed into the GPU with all of the data, so that the GPU can then run hundreds or potentially thousands of parallel processes to be able to calculate the weights and biases in each neuron. So in this particular code, one forward propagation, one epoch as we call it, would take maybe 2 hours. Running on a pretty serious GPU at the university. If I was to do that on my Apple Mac here without a GPU I could easily access and just running it on the processor, it would probably take the best part of a week. So my whole model took on the GPU took about 5 or 6 hours to optimize. If I was running that on my computer here, that would probably take about 3 or 4 weeks. So that's the kind of power that the GPU gives us. And again, this is specific to training. So, you know, I can't sort of reiterate enough that with two aspects of machine learning, here was the aspect of the training. And then once we have the training models where all of our parameters, our biases and weights are optimized, we then use those for the evaluation model. So in the evaluation model, the forward propagation uses the same weights and biases that we found during the learning. But the evaluation model still uses a GPU, but there's no need for back propagation. So the process is much faster. In other words, we don't have to recalculate all of those weights and biases. So that particular model we use, which I'm now using in the evaluation mode, takes only a few milliseconds to run. So this is, again, why machine learning is so incredibly powerful, because all of the grunt, if you like, all of the hard work goes in the data pre-processing, that is taking the data and turning it into something that the model can understand, and then the training. Once you've done all that and you've optimized your model, we can then use all of the parameters to do the forward propagation and the evaluation, and then you can have some much lower level or lighter resource type processes to be able to do that and still give you the right outcome. So some of the challenges we have within training or learning, whichever way you want to look at that, is that we require thousands and thousands of data points. The more diverse the data set, the better. And there's almost a point where you can't have too much data. I mean, it gets to be a technical limit because you can't keep training forever. You know, although some of these models take weeks to learn, you have to stop at some point. Data is presented to the training model, so weights and biases can be modified to provide the optimum prediction or classification. But we do have some interesting challenges. If we're not careful, we can overfit the data. And that means that the model starts honing in on a specific aspect, which is only known to that data set. So once you've trained the data set, you then go and test it with your evaluation data, which is a completely different data that the processor has never seen before, the model's never seen before, and it doesn't work. And that's because you've probably got into a system of overfitting. You can also underfit the data. So that's when you, no matter how much data you throw at the model, it just can't find any patterns. And that could be because there aren't any patterns to be found, or that your preprocessor is incorrect and you've used presenting it with rubbish. But there can also be biases within the data set. And we should be very, very concerned about data bias. So data sets are incredibly important because they're the basics of machine learning. They allow us to learn, they allow us to train, validate, predict, and classify. So we must have data. Tens of thousands of data points. The more data, the better. And the more diverse the data set, the better. So we don't want to overfit, we don't want to underfit, we just want to be able to get the right amount of data. The models must be generalized for all unseen data. So this is, again, getting that sweet spot between having overfitting, having underfitting. We want to provide the most generic model we possibly can so that any unseen data is then can be processed. And in the similar way to the analogy I used to teaching the child to cross the road, we don't teach the child what every single bus in the world looks like, because that would be clearly impossible. We just teach a small set, a generalized view of what a bus is. So we might say it's that big oblong thing with wheels on it and a driver at the front, and that would be our generalized data set. And that's what a data set looks like. So that's just 15 samples from the data I've been using. And the first column you can see there is the actual label. So it's either a 1 or a 0, because this is what I call a binary classification. And then the rest of it's just numbers. So those numbers do relate, they're not just random numbers that have been chosen, they actually relate to TCP/IP flows within a particular data center that I've been training my model on. But they could quite easily be videos, images, they could be audio samples, they could be anything you like. It's just that as the data scientist takes the images and the audio samples or the text or the optical recognition, they then present these to the model as numbers. So data bias. I can't overstress how much you should be worried about data bias. For supervised learning, we've already said that data has a label. So the label is classified by humans. So that label can be anything you like, depending on what you're learning. But what if the human gets the label wrong? And then we have a label, an adult in a jacket. And it could just be that the human classifying this image just happened to get it wrong one day. And if they get it wrong enough, then we have all these kind of interesting images and data sets which are not accurate. So a large part of what we need to be concerned with in machine learning is getting our data set right in the first place. And there are all kinds of biases that we should think about as people before we start classifying the data, because fundamentally, all of this machine learning revolves around humans having got the data classified right in the first place. So in conclusion, ML is providing unprecedented opportunities for broadcasters. The data sets are key to its successful application. Data bias is a major concern, and we should all question the data as we do in life.
Tony, just what at the moment are the applications that are getting real traction, that where we're seeing ML really penetrating the broadcast industry? And secondly, what do you think are the ones just over the horizon that are coming literally in the next year or two?
I think library metadata classification is the big one for the moment, and that's what's been seen a lot. And the more metadata we can add to the library material we're ingesting, the better opportunity we have of being able to retrieve it later on. So that's my first point. Also, video compression. We're seeing a lot of GANs being used in video compression and image processing in general. But I think the really exciting one for me is the director being able to talk and instruct the cameras directly. So have a series of cameras around a stadium and say, track a specific player, and have the cameras being able to recognize that player and track them and provide perfectly framed shots that are tracking the player around the field. I think that's the big one for me.
Are you seeing that? I mean, that's an area that very much interests me. And the paradigm of covering a football match or a rugby match is not actually that difficult to understand. I mean, how you cover the game. Then you get the additional nuances of the story and the interaction between players and referee and players and crowd and what have you. And your talk indicates that there is now technology that can, possibly understand what the referee's saying, understand, God help us if they understand what the player's saying as well, seeing from reactions in the crowd, and actually being able to put that together, because that's what a human director does. How far are we away from that?
Well, I've seen each of those examples you described working individually. What I've yet to see is somebody to plug them all together and provide a finished product. So yes, we could certainly do facial recognition. We can certainly do audio to data translation. And the interesting part is the aesthetics of the actual making the program itself. So that's, if you feed enough finished programs into the algorithm, it should be able to learn the particular traits of a specific director, which opens up whole kinds of new and interesting sort of applications.
Yes, in my case, probably the odd whip pan. Tony, if you look in the chat, there are some questions coming in. Joe Tozer, in your simple model, there was a hidden layer in the real world systems. Would there be multiple hidden layers?
There can be. It all depends on how the model works. So in the application I'm using, there's just one hidden layer, but that hidden layer has 2048 neurons in it, and there are 8 hidden layers in each LSTM. So it all depends on how the data scientists have started to put that model together.
Peter Gordon's asking, to what extent could machine learning colorize black and white programs, increase definition, remove scratches, etc.?
It depends on the data set available. I think colorizing black and white is quite interesting because I'm thinking of the World War I images that we saw, which were colorized, and I think they were hand colorized. So if they can be hand colorized, then there's no reason why they can't be colorized by a machine, an ML algorithm, because you'd have to feed it with data, for instance, of their particular regiment that was, in the trenches. What uniforms did they wear? So if you could take enough colors, enough photographs and images of the uniforms, which I'm sure are probably still available, you could then use that to be able to feed into the engine to be able to then colorize. And for instance, you could sort of say in that particular area, what was the weather like? What time of the year was it? So you can create shadows and such like in the right colors. So I think it's all there. It's just really we're limited to the data available. So if the data is available to do this, then yes, then you can be done. Increased definition, again, that's something that is being looked at in research in how we predict the extra data, because if the data isn't there in the first place, what do we do? Well, traditionally, we just extrapolate that through filters and such like, but with machine learning, we can add an extra dimension to it. I mean, we have to have a data set which is a very high definition data set, but assuming that's available, then yes, we could do that. And again, same with scratches.
Bob Hanscom's asking an interesting question about the teaching of the machine. Does the teaching go from primary school to secondary to university, if you like? So he's asking, yeah. Do you start with the training with fairly simple teaching and then it progresses to more difficult teaching as you would indeed with a child?
Probably. It's a continuous process. So one of the great things about this whole idea is that, again, using the library ingest as an example, we could add lots of metadata to the library materials it's been ingested. But if we get a model which has improved, there's no reason, again, why that model can't be reapplied to the data and more metadata be found, reapplied to the image, I should say. The library material and more metadata being found. So yes, it's a continuous process, and in the same way that a child builds on its prior experience, and then so would a machine learning algorithm if you could present it with more data.
So now we're getting into the tasty stuff. You've already done away with like OB cameramen at sports matches and even the director. Yusuf is asking, will machine learning be able to do advanced editing, write full structured scripts, etc.?
I think, yeah, I mean, we're getting into some interesting sort of philosophical aspects. There's one of my colleagues at the university is doing something called pose estimation. And a very basic level, what they've been able to do is type a specific pose into the engine, say, actor stand up and look at the camera. And a model of an actor then stands up and looks at the camera. And then you can tell them to turn to the left, and they turn to the left and turn to the right. So this is very much in its infancy. The kind of thing we're doing in the university and academia is probably 5 or 10 years ahead of being finished products. But yeah, it's all doable.
I think the question is how quickly. It's not so much if, but when, and how quick will that appear? I suspect if you look at history, probably quicker than we realize. Yeah,
and there also is the question of, should we be doing it? Because can we completely replace human thought, and do we want to do that? That again, those are interesting questions. Can we completely replace a director? I don't think so. I don't think we'll ever be able to completely replace humans using machine learning, but we could probably get relatively close.
David makes the point that machine learning is best targeted at removing repetitive human work. Do you have examples of where that is in broadcast production?
Where would we do that in broadcast production? If we use the remote camera, so for example, facial recognition and tracking, we're getting into a point where that's sort of creative, because the camera operator will be bringing their own creative intent and the director to the actual image. So that's one sort of area. Also, I think library ingest, classification and metadata application to the material we're ingesting. So having somebody sat there tagging thousands of hours of material is laborious to the point of you probably just wouldn't work. But having ML engines, like sort of detect sunny scenes, or the Houses of Parliament or the Empire State Building, I think is an area where we'd see that quite a lot.
My suspicion is that one area where we'll see some early entrants of fairly machine robotic coverage, whether it's sport or conference type coverage, political coverage, is where OTT providers are coming in, and there's far more platforms for content to go out on. And if you can put a machine in to do it, where people probably not so worried quite about the high esoteric end of the content, but just the information and the story, then I think that's an area where we may see that coming in. I put a note here, like all these conversations, the HR aspects, and maybe something that we could do next year. I don't know whether you've got any thoughts on that, Tony, that everyone always says, oh, well, it won't do away with people's jobs, it'll just change their roles. But that's sometimes a little bit of a get out.
Yeah, I think, my sort of answer is a variation on that, I suppose, because what I would say is, as we alluded to it a few minutes ago, that humans are very good at creative tasks, but not so good at repetitive tasks. Hence the reason robots run production lines, because humans make lots of mistakes. Now, one of the interesting aspects of creativity is that making mistakes is good, because it's part of the creative intent. And so if you can have a machine which could be trained to make mistakes, then technically it could it could improve on the creative intent. But then you're into the interesting idea of how do you get the data, and which human programs the data to tell the machine to make a mistake, and how would it know in which way to make the mistake in the first place? And I'm thinking of the infamous story about Alexander Fleming with his Petri dish, and left it out one night and came back and next day discovered penicillin. It's that kind of thing which takes human creativity to new levels, which I'm not sure whether we could program into machine learning, or that could be just me wishful thinking. Interesting
thought, Tony. So I can justify all those bum cuts and whip pans I did on OB coverage as being the creative intent. Why not?
Yeah, well, I remember I worked at MTV many years ago, and one of the camera operators thought it was a very good idea to take one of the handhelds and spin it upside down. And then that became an established part of many of the shots that were being used, because everybody thought it was great. I was crying when I saw the connectors falling out the back of the cameras, but that's the interesting aspect.
Thanks, Tony, for that insightful talk. And it's a subject which I'm sure we'll be returning to in the future. Thanks to all of you for your participation, and my apologies to those of you I didn't manage to get to. We hope that you'll be able to join us again in the future, where we'll explore this subject further. Till then, stay safe. Goodbye.